All right. In this module, we're now going to apply what we've learned about stoichiometric defect reactions and go through some examples. So I'm going to go ahead and there's going to be 3 questions on the quiz that I want you to answer. So I'm going to go ahead and show you those 3, and then I want you to go on and work those yourself and then fill out the quiz and then come back after you do all 3 of those, and I'll go through one by one and show you what I get. So the first one is I want you to write the defect reaction, again, balanced in all the ways we talked, for a Schottky defect in Al2O3. Then once you've done that, you can go ahead and look at the defect reaction for a Frankel defect, and I want you to look at that for 2 materials, NiO, nickel oxide, and uranium oxide dioxide, UO2. And then the last one I'll have you look at is the defect reaction for misplaced atoms in SiC. So go ahead and see what you can do with those 3, answer the quiz questions related to those, and then come back and I'll go through those 3 quiz questions. All right, so let's look at those example problems that are on the quiz. And first we start with a Schottky and Al2O3. We've done the more general case, but let's look at it in terms of Al2O3 or alumina. So as always, we can write null or perfect crystal. I'll accept multiple forms for the reactant side. And then we get to the Schottky defect. And so this is going to create defects on both cation and anion. So we know we're going to have a vacancy of aluminum. And based on this, this is 2 minus, so that's 6, and then so 6 divided by 2, we get 3 plus. So this is going to be 3 plus. And so as always, we can kind of work the math there. And if we remove a 3 plus, that's going to leave us with a minus 3 charge. And then we also are going to have vacancies on oxygen, and we know that that's plus 2, right? So the next thing is we need it to be balanced, right? And so we can balance this by removing a formula unit, right? So 2 of these and 3 of these. So that would be a minus 6 charge and a plus 6, 2 times 3, right? So this balances it out. And if we wanted to be even more correct, right, we could add the aluminum and aluminum sites and the oxygens and the oxygen sites as these go to the surface, right? But I'll leave this as that because this is enough. Okay, so that's the first one, right? We just have to balance. We've balanced the charge. We've balanced the mass, assuming that these aluminum and oxygen are going to the surface, and the site ratios as well. Okay, so let's look at Frankels. So the first one is to look at nickel oxide. And when you're doing these types of questions where we know we have an issue with interstitials and we want to know which one it does, either cation and anion, it's often helpful to look at the structure for nickel oxide, which is rock salt, and also the specific sizes from, for example, the chart in chapter 3. So this one is rock salt, which is a fairly standard structure in that the anions, oxygen, are larger than the nickel. And so that would mean that the nickel, which is smaller, is going to form the Frankel defect. And so in this, we would write nickel in the nickel site just to represent kind of the null or perfect crystal. We could also write that as well. I'll accept either. And then we have a vacancy of that nickel on the product side, and that's going to leave us with a negative charge. And then that nickel goes to an interstitial, and that has a plus 2 charge. And it's balanced because we're just moving 1 to 1. And this, again, when you're looking at the site ratio, interstitials do not count as the site ratio. So we're not creating any sites here. And so again, cation, Frankel, nickel is smaller than oxygen in terms of size. The next part is uranium oxide, dioxide, right? So in this case, again, if you're unsure, go back and look at these structures, right? The structure that we're dealing with here. This is a fluorite structure, and you can also look at the relative sizes. And in this case, the cations are relatively large. And so you can make the argument the oxygen is the smaller species here. Or if they're comparable in size, it could be either one, right? If they're similar in size, then if you expect interstitials, it could be either one. So you could make the argument as to one or the other. So, but for these purposes, I'll do it for the oxygen. And so oxygen from the oxygen site. And so that leaves us with an oxygen vacancy, and that's always +2. And then that moves the oxygen to the interstitial, and that's a -2. So here we're doing anion for this structure. And the oxygen is, I believe they're pretty close together. You could look at the table of ionic data to see, but they're pretty close together. So you could probably write either one of them. All right, so the last one here, we're going to look at the misplaced atoms. And this is the one where I didn't give the expression for the general, but I wanted you to work out ahead and see what you get. So I'm going to spell it out really on the left side just so you can see, right? So silicon should always be on the silicon site if it's a perfect crystal. And carbon should be on the carbon sites, right? It's a perfect crystal. So if we have misplaced, like I said, they're basically swapping positions. And in this case, if they're swapping position, they're really considered atoms, not charged ions, right? So we're not dealing with silicon 4+, carbon 4-. Really, we're just considering them as atoms. And so in that case, instead of looking at the charge of like this is +4 and this is 4-, right? We're really considering them as atoms that are neutrally charged. So in that case, the silicon would go into the carbon site, and because these are both neutrally charged, this will be X. So we're not considering it like this. And then carbon would go into silicon site, and again, they're considered atoms, so they're neutrally charged, so there's no change there. And again, that's the key here, atoms, not ions. So this would only happen if we're looking at covalent materials where they're sharing electrons as opposed to ionic structures where they have definite charge. And so that's the key to these structures. So this is a misplaced, and this kind of goes through those 3 quiz questions in this module.